In class, I gave you this problem. On the left, you see 9 lines, and if you count the number of separate regions, there's 18 regions. You can start here and count 1, 2, 3, 4, and proceed around this way. On the right, there's also 9 lines, but there's a lot more regions if you count them. I think there's 30 or maybe close to 30. The question I want to know is, if I'm trying to make the largest number of separate regions I can with 100 lines, how many regions is that? This problem appears fairly intimidating at first because it seems like there's too many lines to think about, and definitely too many ways of arranging the lines to think about. And even if you do come up with an arrangement of 100 lines, how can you be sure that it's the most regions? How can you be sure there's not some other way of arranging them? So the strategies that we practiced in class were explore this kind of situation with smaller and simpler examples of the same kind of problem, organize your results using another representation like a table or a graph, and try and find and describe a pattern that you can generalize. And here's what we did. Instead of 100 lines, let's start with the smallest number of lines we think makes sense. And a lot of people thought that was 1 line. So if I've got 1 line, I have 2 regions. And then they could try 2 lines. And it seems intuitively clear if you move the lines around, you can think about what are all the possibilities. And it seems like it's not possible to get more than 4 regions. So with 2 lines, we've got 4 regions. For 3 lines, it's a little less clear. A lot of people made a 3rd line that goes through this intersection point, and they got 6 regions. But then one person suggested making a triangle in the middle, and here we've got 1, 2, 3, 4, 5, 6, 7 regions. When you're using this kind of strategy, it's often possible to go one case smaller than you think actually makes sense. And it might not make any sense to ask how many regions with 0 lines, because it might feel like, well, you've got to be doing something, and 0 lines isn't actually drawing anything. But very often, the smallest possible case, a kind of trivial case, still follows the same pattern that you're interested in exploring. So let's do that one also. With 0 lines, I've got a maximum of 1 region, the whole region here. And of course, what we're hoping to do with this information is figure out what's the function, what is the relationship here, or what's a pattern that we could use to figure out this number here, which is the number we actually want. And now we've got a pretty good chance of connecting this to math that we've already learned at some point in the past. So if you plot the points, it looks suspiciously quadratic. Is it really quadratic? Well, think about other math you've learned related to quadratics. One thing you might know about quadratic functions is that they have constant second-order growth. So linear functions, the first-order growth is constant. Quadratic functions, the growth of the growth, the second-order growth is constant. So this is evidence that maybe a quadratic function could fit this data. If you didn't know about that fact, you could test your theory by taking the general form for a quadratic equation and plugging in the xy coordinates that you know here, and then solving for values of a, b, and c that would fit the data that you have. If you do that, you actually can get a quadratic equation that fits the data quite nicely. And of course, once you have an equation, then you can plug in the x value that you don't know to calculate the y value that you want to know. So let's review. We started off with a problem that seemed very large and intimidating, and we used some solution strategies to try and figure out more information about the problem situation. We looked at a smaller version of the same problem, saw a pattern that we could use to answer our original question. Okay, at the end here, let me point out that we didn't answer maybe what's the mathematically most important thing that we should have been thinking about. How do you actually know that the pattern that you saw continues? Because all we did was sketch a couple of examples, we saw a promising pattern, and we assumed that the pattern would continue, and we said, yay, we've solved it. We've figured it out for 100 lines. A mathematician would not say that what we did was solve the problem. They would say that we made a conjecture. We saw a promising pattern, we made a guess about what pattern really describes this problem, and we used our conjecture to make a guess about the answer. For this class, that's going to be enough. But realize that as you continue in math, math is mostly about making logically airtight arguments called proofs. And so if you really wanted to be certain about answering this question, you would need to prove that the pattern that we see here is the true pattern for the maximum number of regions. Someone in class actually went a long way towards that. They suggested that the fastest way to make new regions is to have your new line intersect existing lines. She observed that your line can't cross another line more than once. And if you put those two together, if you're able to show that each new line you add is capable of crossing all of the existing lines, then that's enough to establish this pattern.